Hi friends, in this video we are going to discuss about Hopkinson's test. In this load test we have one is the Hopkinson's test. Of course next one is the field test. Let's see, this is the Hopkinson's test. This is also called back-to-back test. And this is also called regenerative test. What is that? Regenerative. The name itself indicates that it will generate again, regenerate. Let's see. For example, this is my motor with armature resistance and back EMF. And this is my generator with armature resistance and generated EMF. Right? So these are two machines we required in this method. That's why this is somewhat costly. And these two machines are mechanically coupled to each other. This is resistance of the motor, resistance of the generator. Here the current which enters into the motor is taken as, for example, I1. Here the current delivered by the generator, for example, I2. Actually, here we have to take one switch through a voltmeter. If the voltage is equals to 0, then close the switch. Otherwise, don't close the switch. Right? Next one. Here we have a field winding. Actually, here we have a field winding. Is like this. For motor field winding. And here we have a supply. Is like this. For example, I am connecting a voltmeter V. This V is common for all. Of course, here we have a field winding for generator also. This is generator field winding. This is a field winding for motor and field winding for generator. Here the current is called field winding of motor. Here the current is called field winding of generator. To know those values, we have to connect one ammeter here. Of course, take ammeter here also to know the armature current, to know the generator current, armature current. This I1 is nothing but IA motor. I2 is nothing but IA generator. For example, here the current taken as I. From the supply, the current taken as I. From this, I1 is equals to supply current plus generator current actually. I1 is equals to supply current plus generator current actually. This is the circuit diagram for Hopkinson's test. Why it is called back-to-back test? Actually, we are giving supply to the motor, electrical supply, then it produces the mechanical output. That mechanical output given to the generator as the input. This generator will develop the electrical supply. That electrical supply given to the motor as the input. Nothing but this motor and generator connected in reverse. That's why it is called back-to-back. And regeneration is going on. It will supply here, it will regenerate here. It will supply here, it will generate for this. That's why it is called regenerative test. Back-to-back test. Hopkinson's test. Next one. Let's see, in this case, what is the input required here? The input required in this system is very simple. No load losses of two machines. This is the input required. Somewhat input is more than no load test. And here we have two machines. One generator, one motor. Hence cost also high. Not in general. This is the next one. And here this is load test. That's why Commutation verified, exactly. Verified commutation. These are generally the advantages and disadvantages of Hopkinson's test. Let's see here. What is the input to the machine? Input to the machine. The motor input is equals to VI. V into IAM, nothing but V into I1. I1 here we taken as IAM. What is the output of generator? Output of generator is V into ISE, nothing but V into I2. The voltage is common for all. Are you okay? What is the armature losses of motor? Armature losses of motor, I square R. What is the armature losses of generator? I square R. What is the shunt field copper losses of motor? Shunt field copper losses of motor is equals to V into IF motor. Shunt field copper losses of generator equals to V into IF of the generator, and stray losses is equals to how much? This is the question. Finally, I want the stray losses. Are you okay? So here the stray losses is equals to, actually this is the current I in this combination only. So the stray losses is equals to, what is totally input to this system? V into I. Just I am taking. So V into I is equals to stray losses plus still armature losses I1 square RAM plus I2 square RAG. This is the input we required here for this current. I am not calculating these two finally. So tell me, what is the stray losses from this? Stray losses is equals to total input minus I1 square RAM and I2 square RAG. This will give us the stray losses of this complete set. Can you tell me what is the stray losses for motor? Stray losses for motor is equals to complete stray losses by 2, because we are taken here two similar machines. And what is the stray losses for generator? The stray losses for generator also Ws by 2. This is calculation of stray losses is equals to V into I, the total input minus copper losses. What are the copper losses? Armature copper losses. Sir, what about shunt, sir? I not calculated this current. For example, this current is IFG and this current is IFM. I not calculated this one. I taken I. If you take I here, you have to take for shunt losses also included. If you take I here, shunt losses also included. This is simply the stray losses calculation and this one. Let's now tell me, sir, what is the efficiency of my motor and what is the efficiency of my generator? Efficiency of my motor is equals to, I said you, we know the input, we don't know the output. So input minus losses by input. What is the input here? I said you, motor input VI1 minus losses Ws by 2, motor stray losses, and motor armature losses and motor shunt field losses by input minus losses by input. This is generally efficiency of my motor. Are you clear? So very important, efficiency of motor, how we can calculate it. Next one, efficiency of generator. Efficiency of generator is equal to, I said you, we know the output, but we don't know the input. So output plus losses. So what is the output here? I said you, V into I2 is the output by V into I2 by, what is the output? V into I2 plus losses. Stray losses plus armature losses plus What is that? Shunt field copper losses. This is the efficiency of generator and motor. I calculated easily by the Hopkinson test, efficiency of my motor and efficiency of my generator. Are you clear up to now? So this is simply how we can conduct the Hopkinson test on our shunt motors. Is it clear up to now? Like, let's see. Small concept is there. What is the main disadvantage of my Hopkinson test? What is the main disadvantage here? Actually, we are calculating stray losses combinedly and deciding that both are having the 50%. But in this machine, which is generator, which is motor, how we can calculate, how we can analyze? Simply, which is given by the supply is called motor. Or another thing is there, the field current of generator is greater than field current of motor. Nothing but as usually, the stray losses of generator also greater than stray losses of motor, but we are calculating both are same. This is the one difficulty. If you calculate like this, what happens, sir? Actually, we are calculating the generator efficiency and motor efficiency, but actually this is not generator efficiency because we are analyzing for generator Ws by 2, but actually it is greater than Ws by 2. It is greater than Ws by 2 and it is less than Ws by 2 for motor. For motor something is minus, for generator something is added. So actually here we are calculating Ws by 2, but it is Ws by 2 something. So for generator we taken only less losses. So the generator efficiency is overestimation. Overestimation of generator efficiency, underestimation of motor efficiency, because for example the total stray losses 1000 we are taking for motor 500 and generator 500, but actually for generator 600, for motor 400. But in the efficiency equation we taken only 500 watts, but actually it may be 550 or 600. So we are considering less losses. If you take less losses, the output is more efficiency. More efficiency is nothing but overestimation of generator efficiency, low efficiency nothing but underestimation of motor efficiency. This is generally for Hopkinson's test disadvantage. Remember this one. Are you okay? Right? Next one. Next one is that, what is the next concept? One, see here. What is the output of my motor? Output of my motor is equals to input of my generator. Are you clear? What is efficiency of my motor? Efficiency of motor is equals to output of the motor by input of the motor is nothing but input of the generator by input of the motor. Yes or no? Right. What is efficiency of generator? Efficiency of generator is equals to output of the generator by input of my generator. Output by input. So from this input of generator is equals to output of generator by efficiency of generator. Input of generator is equals to output of generator by efficiency of generator. Substitute this on here. Efficiency of motor is equals to input of generator. Input of generator nothing but output of generator by efficiency of generator into input of my motor. Sir, this is confusing, sir. Just wait, sir. Efficiency of motor is equals to, from this, efficiency of motor equal to output of generator. What is output of generator? I2 by efficiency of generator and input of motor. What is input of motor? I1. For clear. So efficiency of motor into efficiency of generator is equals to I2 by I1. I2 by I1. This is simply the formula they may ask you. If they ask you a question like that, efficiency of motor is equals to efficiency of generator is equals to efficiency. That is equals to, what happened? If these two are same, efficiency square is equals to I2 by I1. Finally, efficiency is equals to I2 by I1 with square root. Efficiency square is equals to I2 by I1. So efficiency is equals to, tell me, efficiency is equals to square root of generator output current by motor input current. Generator output current nothing but I2, motor input current nothing but I1. So this is the answer. So finally you can write efficiency is equals to square root of generator output current. Generator output current nothing but I2, motor input current nothing but I1 is our answer when both the efficiencies are same. This is what the calculation of Hopkinson's test. In this calculation, one thing you have to remember that efficiency is equal to square root of I2 by I1, and next thing is that overestimation of generator efficiency, underestimation of motor efficiency, because for generator field current is generally greater than the motor field current. For generator the field current is greater than the motor field current. That's why. What are the advantages? This is generally accurate than no load test. Load tests are accurate than no load test, and commutation also verified. These are the advantages. What are the disadvantages? Costly, because we require two machines, or you know, here we have required one generator and motor, that's why costly. And here the input requirement is greater than the no load test, because what we require the input, the required of the input is equals to no load losses of two machines, motor and generator. This is simply about the Hopkinson's test or back-to-back test or regenerative test. They will ask you a question. The Hopkinson's test is also called regenerative test. Why? Why? Because the output of the motor given to the generator is the input, and the output of the generator given to the motor is the input. That's why both having regenerative property here. That's why this method is called regenerative test. Like this you have to convince. Right, sir? So this is about the no load test. First test, Hopkinson's test. Thank you.